Hi, everyone. Welcome to the second session of the second day of this RSC conference. What a great talk we had from Dan Katz today. And now we have a session about tools and applications. It's a bit of a longer session. We have three speakers that are talking to us for about 20 minutes with 5-minute questions. And then we have two lightning talks for 5 minutes each. And at the end of this, we will have a demos. So let's start with Ben Joey from Manaki Benoit Land Care Research. He's going to present to us the data cube for collaborative analysis of Antarctic geospatial data. Welcome, Ben.
Great, thank you, Paula. So yeah, I'm going to be talking about some work I've been doing over the last probably 18 months on trying to build up a data cube. This is part of the Antarctic Science Platform projects 3 and 4. So to give you a bit of context, I'll talk about sort of the genesis of this, go over some objectives, tools that we're using, how we're implementing this on the NeSI HPC on Mahaweka, and then present some of the challenges that we've faced and some possible sort of solutions for those. So this started with a project to map sea ice presence in the Ross Sea. So this is due south of New Zealand. It's an area of several thousand square kilometres, and we wanted to find out when the sea ice breaks up and the water opens up in sort of several areas along the coast, but just the Ross Sea in general. This is a classic remote sensing problem where you think, oh, this will be easy. There's lots of satellite data. You find the data, download it, pre-process it, analyze it, and then find out that it's not that simple, go to one. But really, it would be nice if we could just skip steps 2 and 3. So what we want to do is find the data and then analyze it and reassess what we're doing, because it's much faster to get the final results from that, and more time analyzing and doing science and less time munging data. So as you could guess from that logo, potentially, the first thing I turned to for this was Google Earth Engine. It has lots of geospatial data ready to go, and I could go from a basic idea to preliminary results in less than a day. And this is only really the third time using Earth Engine. Essentially just writing a bit of JavaScript and you get a live map, which is great. And simple questions like, what's the first day in the year where we get a dark pixel, where you're assuming a dark pixel is water, whereas a white pixel or a very light pixel is ice. And then how many dark pixels do we get in a year? So Google Earth Engine is great because it's easy to create an analysis, but also easy to communicate results and share with others, which is one of the sort of key things that we're trying to do as part of this Antarctic Science Platform, is to encourage collaboration between diverse groups of researchers that don't normally collaborate, or not sort of to this extent. But the problem I ran into was I wanted to try something more complicated, and I ran out of data. I wanted a Sentinel-1 product that was different to what Earth Engine had. I wanted different MODIS products, and I wanted to add some custom weather model data in there. And this is fine if you're just dealing with a small area. You can download the data and then upload it into Google. But when you're starting to deal with sort of areas of this size, it becomes unmanageable pretty quickly. Back to the drawing board and off to NeSI after Mahaweka, where we're sort of used to operating already at Manaki Whenua. But this is in a new area, so we had to sort of start again from scratch. And I wanted to create our own space, a bit like what we've got on Earth Engine, or what we have over New Zealand with satellite data at Manaki Whenua. But yeah, adding more model output, more observations, talking to other researchers and bringing their data into it. And yeah, flexible access and integration. Again, flexible tools as well, and you can bring your own, because we want to encourage sort of interesting research rather than trying to force people to use a certain framework. So the main objective, I guess, was to build a common space where Antarctic researchers could analyze their geospatial data, minimize the time spent on data wrangling, maximize the time spent on science. And so to do that, you get the data all in one place and host it on NeSI, and make sure it's pre-processed, analysis ready, searchable, good to go. So someone can bring along a new PhD student and say, go log into the NeSI Jupiter Labs. Here's an example notebook, and off you go. But at the same time, once they've had a bit of a play with a smaller case study area, making it easier to scale up to that sort of multiple thousand square kilometer analysis. So this is essentially what you'd call a geospatial data cube, which these can come in many forms. The most simplest, they're just a well-structured file system full of sort of fairly standard files. And then you kind of go up from there, where you develop sort of metadata catalogs and have common tools for accessing the data cube. Having those common tools is really important, as we've found multiple times with other projects. When you bring people together where they all use slightly different tools, it's a bit hard to get people to work together in a way that's really productive, because everyone's busy trying to translate between their tool and someone else's tool. So if we can start from a common place but still be flexible, then it does make it a bit easier when everyone's on the same page. What this looks like on an HPC is really important to have proper workflows for downloading, pre-processing, and then ingestion or indexing of data. You need a very well-structured file system and appropriate metadata. Any inconsistencies you have in any of these, as many people probably know, as soon as you start scaling up, it's the problems also scale with the data, and it quickly becomes unmanageable unless you have a good plan and have everything set out. It's nice on NeSI, we can provide a pre-built analysis environment, so we can sort of a couple of commands that new users can run when they start up, and all of a sudden they have access to an environment without having to download or compile or build any other tools. And we also wanted to provide some computation time. So this exists under a NeSI project that has some spare compute hours in it. We use a lot of them for the download and the pre-processing, but removing a barrier of people having to come up with their own NeSI project just to have a bit of a play with some data was a big one for us as well. And then also providing some good user support from a geospatial perspective. NeSI support is great from a NeSI perspective, but then we wanted to add our own sort of layer on top of that. And part of that's around building a good community of people that can help out. And again, having that common tool set really helps with that. So the tools I was using for this, mainly SnakeMake to control the workflow, Singularity for the software environment, some of the built-in NeSI modules as well, but yeah, Singularity was a really easy way of getting some fairly custom Python scripts working, yeah, quite nicely. Spatio-temporal asset catalogs or stack catalogs, the way that we're going to be handling, or that we are handling, the metadata for all the images. And then on top of that, we have a Franklin stack API that enables searching. And you search this with something like PyStack and then feed the results into the Open Data Cube, which might sound complicated, but for a user is about 2 or 3 lines of Python. And this all happens inside of Jupyter Notebooks in the Jupyter Lab environment on NeSI. So the way we glue this all together is researchers identify data sets and come to us and say, I want to put this into the data cube. And then we develop a SnakeMake workflow to download, pre-process, and index the data that goes into the stack catalog. And then the researchers can access that via Jupyter Labs, where they write Python to find the data and analyze and then export the analysis. Because the data cube is just files on a disk as well, it's possible for people to go in there and just download the files to their desktop if they want to have a look at a few of them. I'll go over the data volumes in a bit, but you obviously won't be downloading the entire data cube unless you've got a very large amount of storage. I guess the primary challenge we had to start with was scaling up other people's workflows. So if a researcher says, I want to use some data from IceSat, for example, and they provide a sort of an example analysis that they ran, like a paper, that's good. But at the same time, you have to go from that to a full-on workflow for downloading not just a small case study area, but as much of the Ross Sea region as you can get your hands on, or even the Antarctic continent, depending on the data set. And that's not always easy. A lot of the servers that provide this data are less well, will provide poorer APIs than you might think. And then the software to process it is often GUI based, and there might be scripting approaches that you can take, but they take time to implement and take time to get it going on Mahaweka. So that was spent an inordinate amount of time at the beginning, even just finding out how to download this, like the Sentinel-1 and the MODIS data at that scale. We're talking about 400,000 plus raw input files. And then as soon as you start pre-processing those, it blows up from there. We've currently got about 30 terabytes of data used on the HPC. About 20 terabytes of that is the analysis ready data ready to go. The rest of it is sort of the raw data and a couple of intermediate products. And this sort of equates to 1.5 million files at the moment, which is playing havoc with the inode allocations. When it takes a month to download all your data, you don't just throw it away after pre-processing, especially when you're developing a workflow. You want to try and keep that to make sure that if you want to rerun your pre-processing steps, if someone's not quite happy with the state of the analysis ready data, or it's not quite as analysis ready as you thought it was, then you need to go back to it. And if it's going to take you a whole month to re-download the data again, that's a bit of a problem. And then because I'm spending about 10% of my time on this project, it sort of goes in fits and starts, and you have to make sure that you either get everything off no backup onto project, or it's a really good way of testing out the repeatability of your scripts at that point, where you go away for 2 or 3 months and come back and find out that all your data is gone. And the processing was standard HPC workflow challenges, and SnakeMake has helped a lot with those, which is really good. And ESA Snap is a really common toolbox for processing Sentinel-1 data, and that's not the easiest to get going on the NeSI HPC for a number of sort of boring technical reasons. I've learned a lot about SnakeMake implementing this. I've probably done about 2 or 3 large-scale SnakeMake workflows now, and this is the third one, I guess. From the basics, like don't put workflows in your home directory, even if all the inputs and outputs exist outside the workflow. So if they sit on no backup or project, but the workflow itself sits in home, the .snakemake folder will still fill up your home directory if you do large numbers of jobs. And even if you've done all of that and your home still mysteriously fills up, you've got to check your cache, because SnakeMake likes to put things in there and will blow out your inode limit. Again, this is running hundreds of thousands of jobs over and over again. At the same time, you want to optimize your HPC workflows, so your DAG isn't constantly running over hundreds of thousands of files. And part of that is setting up what I call like init rules that don't rely on that number of files. They might rely on like a dot file that you would put in a folder that has a bunch of files inside of it, as a way of kind of abstracting up from just the sheer number of raw input files. Slurm integration is really important, looking at the cluster status and scancel to make your life easier. And protected is also really important, because if your whole workflow falls over and you have an input file tagged as something that was the result of a download, sometimes it will go through and nuke all of those input files. So use protected. Stat catalogs, not quite as simple as they first looked. I thought it was going to be really easy. It wasn't quite so easy, but they are still really good to use. I was talking about stat catalogs. You're needing to host a dynamic stat catalog. So this is a metadata catalog over imagery. And if you want to make that searchable, which is sort of the whole point of a stat catalog, then you need to spin up an API server so that people can come along and query that with their Python code. This can be difficult to do on NeSI. We're exploring options for hosting the server at Manaki Whenua, but having it hook into the NeSI file system in a way that's both usable but also secure. So that's sort of an area in development at the moment. The Open Data Cube is something that's been talked about for a while now. I remember seeing it at a presentation, probably a conference 3 or 4 years ago. It's come out of Geospatial Australia. It's definitely still under development. The documentation and the features don't always match. If you want to use sort of well-trodden pathways through it, then it's good. If you want to start adding a whole lot of your own data into it, it gets a bit difficult, but they are switching to using stat catalogs in the back end, is my understanding, which is a major step forward because it makes things a lot easier for us and for this data cube. And then it's sort of, I guess it goes without saying, but it's something to remember that building a solution that works outside your usual research group always adds complications. It's always easy if everyone sort of knows what's happening, but then trying to explain things to newcomers can be difficult when they haven't spent 2 or 3 years already working with you, and it needs to be robust. So the current status of the data cube, we've got about 20 terabytes of analysis ready data in there that's good to go. The downloading and pre-process workflows for those 2 products have been completed, and they've sort of formed a good skeleton for adding further products. The Jupyter lab environment has been set up, and yeah, big shout out to NeSI support for making that really easy to sort of add custom environments, particularly with singularity containers and specifying your own arguments for those. I was really surprised at how simple that was to do. It was great. The stat catalog is in progress. We've got a basic one, but we sort of want to flesh it out a bit more, but with a bit more metadata, just looking at different kind of add-ons to use for that. We have some beta testers lined up, ready to go. Not quite ready to unleash them on it yet. We just need to get the Stack API up and running. And as always, documentation is a work in progress, but it has not been forgotten. Yeah, so that is my presentation. Yeah, are there any questions?
Thank you so much, Ben. I did have a few questions prepared when you were not here. Yeah, one of the challenges that you did not mention, and I wanted to hear a bit more, is about dependencies, because you're working with multiple users. How did you solve the problem when somebody asks you, I want this other library, and then do you have to restructure some things? Was it easy to add things to provide the service? Can you tell us a bit more?
So far, everything we've done has been via Conda in Python, which makes that a lot easier to work with. Conda's got a lot of really strong geospatial libraries built into it already, and you can always integrate pip packages as well into that if you need to. Again, this is all very Python-centric. We haven't had anyone really trying to hit it with R yet, and that could be its own set of challenges, although people can sort of sort their own R environments out, which is nice there. Anything beyond that is going to be a your mileage may vary, essentially, for the users, although we'll provide support for building singularity images and helping them to integrate those into the sort of the Jupyter Lab setup as well, now that we have some recipes for doing that. So yeah, that's the way we sort of address the dependency issue. You might be muted, sorry.
We do have another question from Maxim. He's thanking you for your talk. Have you considered intake, which is for the catalog part? Intake is package, I'm guessing.
No, I haven't heard of that one, sorry.
Okay, maybe that's a discussion for Maxim and you to follow up.
Yeah, definitely. I'm always open to new suggestions. And I have to say, I might preempt you, but I did see Hillary's comment in the Q&A about Silk, and that had been on my list of things to try a couple of years ago. I went down the SnakeMake route now, but having gone through the challenges that I've gone through with SnakeMake, I am seriously considering whether it's worth jumping to Silk. But I'm waiting for a colleague to finish trying that before I do it, because it's not a minor undertaking at this stage, which is yeah, you got to be, I guess, cautious of the sunk cost fallacy, where it's no point kind of keep putting work in if it's just going to be more difficult to go with SnakeMake. Sometimes it is better just to jump, but just have to figure out what the cost is for that.
NeSI, Callum's NeSI will help you that transition if you want to go through that road. Thank you very much, Ben, for your talk, and we will go to the next speaker now. Okay, now we have Gemma Mason from NeSI, who is going to talk about developing a package to fit piecewise non-linear curves. And then we'll have questions for Gemma.
Kia ora koutou, ko Gemma Mason toku ingoa, and I work at NeSI, Taihoro Nokurangi. You'll have to excuse me. I am getting some lovely help from our lovely tech support because I couldn't share my screen. So I'm going to have to manually tell people to change the slides. So that's what's happening if I have to keep saying that. So next slide, please. So today I'm going to be talking to you about developing a package to fit piecewise nonlinear curves. And this is work that I ended up doing because I am a data scientist here at NeSI. So I move in between research groups depending on what people are doing and when people have interesting data problems. And next slide. The problem that I was introduced to by our air quality group was that they had 5 days of CO2 data from 55 different sensors in classrooms around New Zealand. And they wanted to look at the behavior of the CO2 in these school classrooms over the course of a day, because this can tell you something about the ventilation. So you have input of CO2 from people breathing out, and that will vary depending on how many people are in the room and their level of activity, how much breathing they're actually doing. And then you have CO2 leaving the room to equalize with the exterior atmospheric concentration through ventilation. And if those two things are constant, then we have an expected behavior, which is basically exponential. So there's some sort of expected steady state based on an equalizing between the input and the output, and you will either rise exponentially to a steady state if you're not yet at it, or if there's suddenly fewer people or more ventilation, you will drop exponentially to that new steady state. So if you look at the time series here, what you can see is this is a secondary school classroom. So there's a morning and an afternoon, and then some stuff that happens after the students have gone home, but teachers and so forth are still coming in and out of that. So we've got this drop in the middle, which is over the lunch hour, and maybe also an empty period before the lunch hour if you're trying to interpret what's happening here. And you can see that there's a very beautiful exponential curve there actually. And if you look more closely, maybe even some little exponentials inside the big exponential. So sometimes we do get this expected behavior, and sometimes we get quite messy things as well. And we have to decide, when do we fit an exponential? Can we automatically fit exponentials? Can we detect when there's a sudden change? How do we split up this time series in order to analyze it? So if we go to the next slide. So this is known as time series segmentation, which is algorithmically choosing change points in a time series. And there are many algorithms for doing this. So you can have an online algorithm, which is where your data is coming in real time, and you have to decide if you've just seen a change, which is what we're dealing with here, where you can just see the entire time series and you have to decide. You could do a sort of a dynamic programming approach where you've got some cost function and you consider every possible set of change points and try to satisfy it globally, or there are heuristics that you could use to speed things up, like doing a top-down thing where you sort of pick them one at a time, or a bottom-up thing where you split it into small pieces and then merge. You can have Bayesian approaches where you look at what's happened before and you say, what am I expecting to happen? How unexpected is this new point? There's a lot of different approaches that are used here. But if you look in the scientific literature, mostly what we see is that the most common situation that people analyze is one where we're looking at a change in the mean of your time series. And that's not what we're looking at here. We don't really care about, did the mean CO2 concentration suddenly change? Mostly what we care about is, were we going on a nice exponential that then changed? So we don't want to break up an exponential drop in the middle just because suddenly the mean is much smaller than it used to be. We want to be evaluating, when did the underlying function change? We want to fit a piecewise curve, essentially, where the pieces of that piecewise curve are exponentials. And there's a lot less literature about that. But there is a very nice program in Python or a very nice Python package called Ruptures, which is what I use to produce the picture you can see here. And that is just looking at mean changes, and that's not what we want. But we can. So if we look at the next slide, we can customize this existing software, which is mainly set up to find changes in the mean of a time series, by creating a custom error function that actually just looks at your prospective subset and fits an exponential to it and then says, how good is the fitted exponential? And that's your error function, your custom error function. It's a bit involved, but if you're talking about good, fair, and beautiful, customizable, modular software, Ruptures is just a beautifully excellent package. And so even though this isn't what it was designed for, it is so good that it allows that kind of modularity, and we can actually do this to try several different search algorithms with this custom error function to see how it works. So if we go to the next slide. So there are a number of different algorithms to choose on that Ruptures can implement for us. So binary segmentation, for example, is a top-down algorithm that recursively looks for the best single change point in a given segment. So it splits it up, and then it splits up the split it up things, and then it splits up the split it up things. There's also bottom-up, start with many small segments, choose whether to merge them or not. There's a sliding window approach where you can look within a defined window to either side to determine if this is a change point, just based on roughly what are you seeing in some fixed window to either side. And it can implement full-on dynamic programming, although that is a little too slow for us and probably not an option. There is for piecewise curve fitting in the literature. There's not a lot out there, but there is at least one very nice paper, which it's titled An Online Algorithm for Segmenting Time Series. The reason it's a good paper is that it actually bothers to review existing offline algorithms for specifically linear regression over curves. And it tests a top-down thing, which is basic segmentation, a bottom-up thing, and a sliding window. And it finds, and there are good intuitive reasons for this to be the case. Specifically, if you're thinking about fitting a curve and you're trying to do it from the top down, if you think about that entire time series, the question of if I split it in two, which are the two best exponential things I could, really very relevant here, what the eventual exponentials are going to be. The first few splits you do, if you've got something that's piecewise linear or piecewise exponential, even worse, the first two things you do are not going to be good. You're not really at that early stage. Whereas if you're doing it bottom up, then you hope that locally the piecewise thing isn't even coming into it. You hope that your tiny little segments that you started to are mostly within your pieces. And so a lot of the places where the fit is good is because you genuinely have found a place where you shouldn't have a change point. So you're starting with good information rather than bad. So there are good intuitive reasons to use bottom up. And in fact, I won't bother showing you, but empirically, it clearly is a lot better when you try it with Ruptures. So let's take a look at how it went using bottom up with Ruptures and this customized error function. Next slide, please. So we changed the threshold for allowing a change point by increasing the penalty. So you can see two different options here. The top has a penalty of 50 and the bottom has a penalty of 1. So a lot more change points there. And you can see with the penalty of 50, it's not bad. There's a few places where you can see, yeah, maybe we could fit an exponential curve there and it would make sense. There are also some things that it's very definitely not picking up on, though. Like there's a bit of a peak and an outlier before a straight line going down quite early on. And even with really low penalty, even when it starts breaking up big things in ways that we might not like, it still can't really pick that up. Don't know why. But it's not bad. There is, however, at this point, a confession that I need to make, which is on the next slide. Can we see it, please? Confession. I didn't know I could customize Ruptures to do this. Like, I found Ruptures. It was great. I was like, wow, what a great program. Mostly it's shown me that this is not doing the right thing and I'm going to have to write my own. It's not obvious that you can customize the error function in order to make it work this way. But by the time I noticed that I could have actually done this all along, I had already written my own code. Drawing purely on NumPy and SciPy, and drawing on that paper I mentioned earlier, which was doing piecewise linear curve fitting, modifying their approach to do piecewise nonlinear. So a bottom-up approach, and messing around with when do you merge things and when do you not, what are good conditions for that. And I'd been experimenting for so long that I'd put in quite a few improvements by the time I compared to, well, what if I just customize Ruptures? And so if we come to the next slide, you can see my fit for this particular time series on the bottom here. And what you can see is that it picks up quite a lot of small details. So where there is that bumpy outlier, which you can see is the first purple segment before the straight brown one, it picks up on that. It picks up on a tiny little bit of an exponential before that huge hump in the afternoon where one person has come in and then gone out again, and there's just that little drop. It can find that. The reason it's good at this, the biggest thing that I ended up making as an improvement in order to make it able to do this is when you're trying to decide whether to merge things. Ruptures uses a thing based on log likelihood, which was built entirely for, is this changes in the mean of your sequence? That is what it looks for. Or it's not what it looks for, but it's what it's built for. The log likelihood function that you're sending your error thing into is totally based on things that were built for changes in the mean and not thinking about when do you want to fit curves. The paper that I was working from used maximum error. So the idea is that you merge two things if the error with your new fitted curve is not going to be higher than some threshold. And that's quite good, but it sometimes fails to deal with the fact that you can have areas where you've got a lot of noise and areas with less noise. And if you're using a single maximum error across your entire time series, you can't really deal with that very well. I ended up using statistical significance, which is to say, if I were to compare these two things, is there a statistically significant difference between the things to one side of the change point and the things to the other side? And that is an existing statistical test that is out there. And I had to implement a few careful things based on the fact that I was essentially considering every possible change point. And so you need a higher threshold. Basically, I just implemented that according to standard statistical theory and found that that meant that it was better at pulling out very small things like that little bump before the start of the afternoon. So what that meant was my code ended up being a lot better than customizing existing code. And I think that there were reasons why this was true for my problem. So next slide, please. If I had known that I could just customize Ruptures, would I have written my own Ruptures? Would I have written my own package? I don't know, but I'm really glad I did, because this is a problem for which there is very little specific existing literature. This is not a problem that I have seen handled directly. Piecewise linear is about as complicated as it gets, and there's not even a lot of work on that. The problems for which this software package was written are significantly different, and it's not remotely optimized for the problem that I was dealing with. It's very customizable, it's beautifully written, it's a great package, but there are some things it can't do. Like, for example, I couldn't write a custom error function that implemented the statistical significance test that I was doing, because it would need to consider the next merge, both the two existing merges on either side and the merge thing as well. And the custom error function can only consider the segment that you're looking at. It can't consider the segment you're considering merging with. It's not built in for that, because although this is a beautifully modular package, that would be a bit much. So there's no obvious way to implement that, because the people who wrote the package weren't thinking that this was something anyone would ever need to do. And so if I had been working with existing code, the existing structure wouldn't have made it easy for me to try new things. And it turns out this is a problem for which you want to be trying new things. And so I think this is an important principle when you're asking, should I use the existing software? Should I write my own? One of the most important questions you can ask is, how new is what I'm doing, and how new do I want it to be able to be? And when there's not a lot of prior work, you often find that even when it's really good to know what the existing things can do, it's better to have your hands in the little details and to know that you can just go in and change a thing because you wrote it and you know where everything is. Next slide. So the outlook from here is I got handed a really interesting problem. And big thanks to the air quality team for handing it to me. There's some existing work on piecewise linear curves, but not much beyond that. And that means there's a really big opportunity to try and develop new things. My code's not yet publicly available. If you have a use case, feel free to send it my way, because I'm still really interested in this as a subject and applications where it can be useful. And I do plan on putting together a preprint. And once I have that, we'll be able to make my code available and hopefully make it, if not as good as a beautiful package like Ruptures, at least usable to the general public. That's my hope here. So thank you very much for your attention, and I look forward to hearing your questions or thoughts.
Thank you, Jenna. What a great presentation and journey you have shared with us. I'm really glad that you have tried and tested and created a new thing, and I'm looking forward. We do have a question from Bridget Armstrong, and I think you kind of mentioned this, but if you want to add something, how did you decide statistical significance? Did you use multiple test correction?
Yes. So there is a thing known as the Chow test, which is looking at, so it was originally developed in economics for when do you put a change point between two things. Is there a statistically significant change? And it was built for, say, for example, do you want to know if a presidential election affected the stock market? Well, you test change point presidential election, stock market before, stock market afterwards. Is it a statistically significant change? And you are correct to know that you note that you really do need a correction for multiple tests if you're using the Chow test on every possible change point instead of just one. So what this means is I used a Bonferroni correction, which is one of several standard ways to statistically correct for this. And I found that certainly in terms of the results that I was seeing, I got something that looked reasonable after implementing that correction for multiple tests. And yes, without the correction for multiple tests, it will always tell you that it's statistically significant pretty much, because you have gone through and selected the best out of every possibility. And so you will get nonsense if you just say, well, is this statistically significant if it was the only thing I was testing? That's not a useful question to ask. You do need the correction.
Okay. We do have another question, and just 1 minute to answer this. Wolfgang says, great talk. How computationally intensive is your code in terms of runtime, CPU, any other requirements? Can it run in a laptop?
So I was running it almost entirely on my laptop. With that said, I was sometimes running it quite patiently on my laptop. It really depends on how many points you're trying to analyze. So the original data was every 5 seconds, and that would take a good, 5 minutes type of thing. But also we were often collecting it into averages over 1 or 2 minutes, and that was running in reasonable times. Like there'd still be a bit of a pause, 30 seconds or so, but you could put up with the time it took. So moderately computationally intensive, but not prohibitively so.
Okay. Thank you. With my timekeeper ahead, I'll need to stop the questions. There's a really good question that I also like to ask about interactions with Rupture developers, maybe, but we can have those questions answered via the hub. I think we'll go back to Ben. Thank you so much, Jenna, for sharing with us.
Thank you very
I'd like to welcome Rose Pearson from NEWA as well. And Rose is going to talk about automated generation of hydrological condition digital elevation models for the national scale hydrodynamic modeling. Welcome, Rose.
Koutou katoa, ko Rose aho. I'll be talking today about the automated generation of hydrologically conditioned digital elevation models for national scale hydrodynamic modeling. And this work is part of the Mā Te Homaru, or Te Wai, which is a large endeavour funded project. It's currently in its second year. And the focus of this project is on producing nationally consistent flood maps. And it's really focused on river flooding. And that the aim, I guess, is to improve Aotearoa's flood resilience. Flooding is important. It's internationally and locally frequent and expensive. It's getting worse with climate change, and we just need to read the news. So these are flood events in the last 7 years, including about 7 probably from this year. And of course, this is all backed up by scientific literature. Flood inundation maps, these, I guess I've mentioned that, and by that I mean the depth and extent of floodwater, surface floodwater. And this is a really useful tool for planning, prediction, and response to flood events. So it could be that you've got, say, the storms that happened July and August. There's a big, weather event coming, and you can sort of use flood modelling to predict, given the forecast weather event, how much rain's going to come down, how much water, is going to come down rivers, and what sort of surface flooding you're going to get. Or you can use it for planning, say 1 degree of increased warming, what impact will that have on our sort of cities and other infrastructure. In this program, we've used 2D hydrodynamic modeling, as it's more accurate than other sort of approaches. And thing to note here is these 2D modeling tools are based on a square grid. And that the hydrodynamic modeling is really highly dependent on the digital elevation model. What do I mean by a digital elevation model? This is a digital representation of the bare ground topography. So this is with trees, buildings, and other ground cover excluded. You can see in the sort of the upper image here, we've got a bunch of blue points. Those are representing sort of elevations, in this case probably from LiDAR, and we're really interested in the ones that are on the ground, and you can see this red line that's mapping the sort of the ground elevation, and that's what we're talking about for a digital elevation model. Hydrological conditioning is a process of improving this digital elevation model to represent the flow paths so that it more accurately represents what water will experience, so the flow paths of water through the removal of spurious obstructions. So these can be things like culverts or bridges. If you look at the image here, you can see my mouse. Here we've got like a little ditch, and you can imagine there might be a culvert here, and depending how you're measuring the elevations, you'll measure the top of that culvert. That's not what the water sees. We want to represent the bottom of that culvert, as that's where the water will flow. Before we sort of talk about the approach we've used, I wanted to sort of discuss the data that's available for digital elevation models. We've got LiDAR, and if we look sort of here, we've got basically LiDAR. There's a laser scanner underneath the plane, points, the laser sort of shines down, and the reflections are measured. So you get points on the surface of the of the land, anything that, you know, is looking up towards the sky. So we've got some reflections here off the surface of building, off the ground as it flies over trees. We'll get reflections off the top of the trees, but also where you can see the light through the trees off the ground as well. And this produces a 3D point cloud, sort of unstructured data. We've got global DEMs, which you can sort of see in the bottom, and these are generally produced from satellites. The resolution's generally coarser, we're talking more like 50 square meters for each of those squares, or 50 meters on each side for each of the squares. And depending on the satellite technology that's been used, there's different artifacts. So it might be that these are representing the tops of buildings and trees. That's generally the case. They often have slightly greater vertical inaccuracies. So typically without some sort of improvement, they can't be used directly to produce the high quality sort of flood modeling that we're aiming to do as part of our project. Other sort of forms of data that elevation data we're interested in are ocean depth contours and river depth cross sections. This is because both the global digital elevation models typically, and also sort of the most common form of LiDAR, they don't really give you any information beneath water. And the water sees the bed or the bottom of rivers, as well as we mentioned before, culverts, things like this. And of course the ocean. Green LiDAR, I've noted here, is a sort of emerging form of LiDAR, and this does penetrate through water. So that's really gold standard. And there's a few sort of green LiDAR devices in Aotearoa at the moment. They're generally used in kind of research. I know Christchurch University, Canterbury University has one, but at this stage, there's not widely available data. And then I've noted down here, I've also noted bridge and culvert locations and also river networks. And this is really focused on hydrological conditioning, as those are areas we really want to make sure there aren't any of those spurious obstructions. And just before I go on, we've got a bunch of mixed data here. The LiDAR is great. That's sort of best case. It's not everywhere. And we have a challenge in bringing all of this data together, bringing in ocean and riverbed elevations where they exist. Unfortunately, many, perhaps most of our rivers in Aotearoa we don't have cross sections up their length. So we also need a process of estimating what those bed elevations are. And we also sort of, need to be able to bring in, ensure that we don't have spurious bridges or culvert obstructions. So to address this, we've produced a package called Geofabrics, which I sort of covered last year in its very early forms. And this is becoming mature. It's sort of got its full form, and it kind of does everything we need to do. But of course, there are still a few areas of ongoing development. It's an open source Python package. And if we look at the green boxes here, we've got unconditional DM generation. This is focused on taking LiDAR point clouds, these global digital elevation models for areas where there isn't LiDAR, kind of combining them together and taking the unstructured point clouds that are LiDAR points and sort of basically averaging them into a structured digital elevation model. That produces an unconditioned digital elevation model. And on the same level, we've got two other processing sort of boxes. We've got riverbed estimation and drain and culvert bed estimation. So that's for really trying to produce bed elevations in areas where we don't have measurements. So this is to be applied on rivers where we don't have river elevation cross sections, and also to drains and culverts where those elevations aren't captured in LiDAR surveys. And then at the bottom, we've got hydrological conditioning, which is a processing step sort of focused on combining the unconditioned digital elevation model with any measured or estimated bed elevations. And the we've got that sort of, we're trying to maintain flexibility here. So this can be applied, the same process can be applied all across New Zealand, whether or not you have direct measurements or you're having to estimate these bed elevations. Oh, sorry, one last thing I wanted to note. We've had a focus on, well, using open access data wherever possible. So the OSM sort of acronym that stands for OpenStreetMaps, which we have used to provide our river, drain, and culvert alignments. A real benefit there is we can kind of supplement that in a sort of publicly accessible way, so others can use sort of our work in the future. So I'm really going to skim over this area. I'm not going to go into details, but this sort of slide showing, I guess, the general, well, a snapshot of the approach we've used for estimating river depths. Big challenge, of course, is estimating this where there are no cross sections. And we're basically using LiDAR data and river network flow and friction together to produce estimates of bank width and slope, and then some hydrological equations that kind of relate all of these values to depths. And then from there, we can go to river bed elevations. And as I've said before, this is basically something we can do at the national scale, at least where there's LiDAR. So that is a limitation. And again, not going to go into details, but I just want to sort of show that we have spent some time validating this approach. So here we've got two plots in the Waikanae region, just showing our validation against some measured cross sections, which we've applied here and at a few other rivers. So the sort of orange and green lines are looking at kind of error compared to the cross sections, while the blue line is an unconditioned DEM. And the two plots, the upper one is looking at the section depth. So at each measured cross section, at each point where it's measured, what's the error between the measurements and our produced digital elevation model. And in the lower plot, we're actually looking at channel area as, from a modeling perspective, a hydrodynamic modeling perspective, we care about the cross-section area of the channel because that determines how much flow is going to go down the channel. Wanted to provide a visual illustration of the impact of this hydrological conditioning process on a digital elevation model. So in this slide, we're looking at the Waikanae River mouth. And sort of a figure, or in part B of this figure, we have an unconditioned digital elevation model. So this is just directly from LiDAR, where we've taken, all the points. I think it's at a 10 by 10 meter sort of square. Taken all the points in those squares, performed an appropriate type of averaging, and we have a single elevation. And out here, sort of reflections off the ocean. In sort of part C, we've just included the ocean bathymetry. So we've got these ocean contours, and we've sort of included those elevations to produce our digital elevation model. And you can see the dark is where it's deeper, the elevations decreasing. In D, we've performed our estimation process for estimating riverbed bathymetries, as well as a transition into the ocean. And this has been incorporated into the digital elevation model. And then in E, we've included our drain and culvert elevations that have been scraped from OpenStreetMaps kind of within the region. And these have been included as well to remove some of those obstructions. So in this slide, I just wanted to kind of touch on the changes to flood inundation between an unconditioned and conditioned digital elevation model. So again, won't be going into details, but in this slide, if we look, well, it's basically showing the impact of hydrological conditioning on flood inundation maps. Thanks. Here we're in the Waikanae area, and the figure to the right shows the change in flood inundation depths in meters of water as the unconditioned DEM is replaced with the conditioned one. You'll have to trust me, and I'm trusting our hydrodynamic modelling friends that this is an improvement. But you can really see there's quite a substantial change in areas away from the river. So it's quite important to this. I think it illustrates the importance of the hydrodynamic modelling process. I really like the FAIR acronym that was shared by our keynote speakers earlier in this conference. And I guess for me, the rapid advancement of this sort of development of this package is only possible because of the various FAIR Python packages out there, particular NumPy, Xarray, Rio Xarray, which is built on Xarray and Rust.io, Dask, and it's just phenomenal. They sort of tick, I'd say, all the boxes: findable, accessible, interoperable, and reusable, and have really accelerated our development. In turn, we've been able to use GitHub, its wiki, things like Sphinx for documentation, GitHub Actions to hopefully make our code more accessible to others, more findable. We've also sort of explored, and this was definitely a new area for me, publishing our sort of code using both CondaForge and PyPy, the Python package index. And if you've developed something like this, and maybe it is new to you, I really do encourage you to search for either of those. They've got some really great sort of, I guess, websites or web pages for taking you step by step through the processes you need to go through for perhaps reconfiguring your package structure and then publishing it. CondaForge is curated and PyPy is a bit less curated, but they're both, great options. Cool. The only other thing I wanted to note is it's just great to be able to use open data like OpenStreetMaps, the Lens data service from here in New Zealand, and also Open Topography. Thanks all.
Thank you, Rose. What a great presentation you had. I am seeing a lot of people interested in hydrology models. We do have time for one question, and it's Bridget Armstrong again. Could you incorporate wastewater networks in urban settings to your project?
Oh, definitely. That's, I guess, an area to look forward to. Depends on the, I guess, but yes, I guess is the short answer. It'll require a bit more work, but the way we've set it up means it would effectively be a separate module to the side that could be included in the sort of final hydrological conditioning step.
Awesome. Thank you, Rose. An agreement with the discussion forum from Alexander. Great to see the range of open source tools that you are using. And if other people are in the audience not researching hydrological models, then maybe you have time to talk about the tools that are being shared across different domains. Thank you so much, Rose. We will go to our next speaker now. And we have Phil Morod to talk about flood data management system in New Zealand. Please, Phil.
Hi, everyone. Tēnā koutou katoa, ko Phil Morod, tuko ingoa. My name is Phil Morod, and great pleasure today to be part of this conference and happy to present the work we are doing. And what I would like to present is a new decentralized data management model to fit the challenges in a multi-agency collaboration in flood management in New Zealand. It's a very long title. I'm sorry about that. So maybe I just wanted to just give you a bit of a background. I'm presenting on behalf of two organizations here, the Waikato Regional Council. I am a senior regional hazard advisor and also a researcher at the Ipu Te Mahara, the Artificial Intelligence Institute at the University of Waikato. So the easy way that I said, I've got a long title, sorry about that. The easy way to show you what it is about is showing you a data flow, a workflow of the project, what we would like to achieve in this project. So it's going to be about natural hazards and flood again. So a very great talk from Rose just before, so I'm going to speak about flood. And we are I'm going to present the work that we are doing for modeling flood for the use of an emergency operation center, which is dealing with flood in real time and having a data-driven approach. And the output of this is that we can get informed decision and making better decision making for how we can deal with flood. I would like first to present the team working on Nick, Guilherme, Justin, and Paul under the supervision of three professors at University of Waikato, specialized in AI, artificial intelligence, Albert Berner and Abe. But probably to give you a bit of understanding how does that work fit into, I would like to present the TIO project. So the TIO project is a 7 years funded by MB data science program. We are in year 3, so started 2.5 years ago. So it's still 4 years to run. And the purpose is to first developing advanced tool for analyzing data, especially in the environmental data. And the second one is to create a platform for organizing and accessing the data. Just to for more clarity, I just want to say that TIO doesn't store any data, so it's just a catalog of data. So we have a lot of people working in the TIO project. It goes from data scientists to environmental scientists with software engineers and a lot of PhD and postdoc and students. So what we would like to use in these TIO projects, first, something we would like to speak about, something that people care about. This is very important. But we have two main challenges about data, what we are going to use. The first one is using large spatial and temporal resolution and coverage. And the second challenge is using ongoing collection, data streaming in live. We have a platform data, so I'm not gonna speak along of the TIO, so please connect on tio.ai. There is going to be a new website coming soon in end of October and November, but this platform is the vision of having a community, and in this community, we would like to bring people, expert, to practitioner and beginner. And in this platform, we have a few useful information. It goes from data set as well before, the repository of data that you can find environmental data if you want to work on, but also we're sharing notebooks, Jupyter notebooks, that you can use that code written by different people from the team, and you have access to a few tutorials as well. So if you are a beginner, you can start somewhere using some data that you have and maybe a bit of a script that you can adapt for your own purpose. So why flood? It's important. You have seen that with the presentation before. It's important, but when I started a year ago in the project, it was in 2021, and I used to say, "Oh, 2021 was the worst. We were beating a record according to the Insurance Council of New Zealand. The amount of total insurance claims was up to $324 million, and it was beating a new record, which was in 2020 with over $270 million. So it's important. It's a lot of money for New Zealand to repair the damages of flood. So what can we do? So how 2022 is looking, and according to the newspaper and what we have seen so far, is not very good. New Zealand is on track for a worst year ever for climate-related insurance claims. And a post from the Insurance Council of New Zealand in the beginning of July saying that at the end of June, the total insurance claims related to extreme weather was near $200 million. and it doesn't count what happened in July and August. And we know that July was the wettest July on record. So a lot of flooding happened across New Zealand in July and August. Of course, we had this huge flood in Nelson that some location some of the location near the Tasman and Nelson get 2 times, 3 times the average, the amount of water rainfall that they usually get in the months in only 3 or 4 days, which is huge. So here we come. We are we want to develop a regional flood impact prediction tool for the Waikato Regional Council, which is in charge of the operational flood management in the region, to help them making informed decisions. So when we started the project, we thought that it's going to be just a kind of machine learning exercise, trying to find good algorithm and fitting to the data and see what we can predict. And it was working well. Actually, our first models using classical machine learning algorithm, as we can see on this curve, the blue curve is the observed data, and the orange curve is the 3-hour forecast of the river level, and it showed that it's not bad. So it was promising, and then we need to make more progress, of course, but it was looking good. It was looking good for so far. So we added more data, and then more data, a bit of more accuracy in the modeling. And this is another example where we used another source of data from mud service in correlation with the hydrology core data from the regional council, and it showed that we are much better in the forecast of the next 3 hours. So just a very quick overview of our latest model, which use the LSTM machine learning tool, which is long short-term memories. And what we want to show here on the right side is the rain gauge, the rain radar provided from Met Service, which give us gridded rainfall information, which we fitted to our model. And what we have on the top left side is, again, the blue curve, which is the observed data. And in orange, the variation is showing the different output of the model according to some variation on the parameters. But at this stage, we were very happy with promising results. The LSTM was performing very well. But one thing that we should be aware when we want to get into decision making, which is important for decision making, is about uncertainty. So we started to fulfill this missing point, and using a Bayesian approach from fortnight all. And we wanted to quantify the uncertainty, which was very important. This is what we do. So it's what we show on the left bottom plot, with the dotted line giving us the range, the 10-90% quantile of the model. So what we learned is we were quite excited because it was performing well, but it was a bit hard, to be honest, to tune the model into a real-time application. So this is where coming into the game, the way that we wanted to deploy our model to, for instance, the regional council, to help them to manage the flood in real time. So we used some of the tools we have been hearing along in this conference. We use Mercury and Streamlit, that's some open source framework that giving you the opportunity of converting a Jupyter notebook into a web application, and that's it. Very easy. That's not the end of the talk, but I was thinking it was so easy. But this is where we started to find a few difficulties that we didn't think about it at the beginning. But to understand how we can deploy a model into an operational room, an operational service, we have to understand a little bit more about how we manage flood in a region, for instance, the Waikato Regional Council here in New Zealand. So we have in the middle that we call the EOC, the Emergency Operations Center. This is the way that we collect all the information available and we providing intel to different organizations. It could be stakeholders, so district council, it could be civil defense, it could be DOC, Department of Conservation, Wakakotai as well, and ZTA for the road management, etc., etc. So what fit into this EOC is the hydrological data from the Waikato Regional Hydrological Network, and of course weather information, which is in New Zealand, provided by the official weather provider, which is MetService. And then we have people here like me analyzing all the data and trying to make good information of it that we can distribute to our stakeholder. And this is where, in the middle of it, that I would like to see the model helping us to make informed decision. But it's not easy. So there is different challenges that we have to think about when we want to deploy a model. First, where we should deploy the model at the data source. It's very easy if we have only one data source, but what if we have multi source of data of input for our model? So, and then it comes to different question about data governance, data from numerous sources with different workflow and data handling practices. And of course, we want data that is reliable and consistent for as an input for our model. And we, at some point, we have to think about that approach protection. So this is where we think about data management solution. What can we do? So in very very recent, actually, the last 2-3 years, we started in 2019. We started to use the term data mesh, and it comes from a concept that has been created by Zamak Degani, which I brought the front page of the book here. Very good. And Zamak, she was trying to find a response to growing number of data sources and the need for business agility. So this data mesh concept totally fit our requirement, our challenge that we would like to get over it. And what is data mesh really? It's based on the principle of a decentralized or distributed architecture exploiting a literal mesh of data. So it's different approach from the data lake or data warehouse that you probably have heard or use until now. But the big thing about data meshing is that we would like to access in real time to the most up-to-date information possible. So very quick, I just want to add that data mesh is not a software. If you don't know about data mesh, it's not a software, and the concept of data mesh is technology agnostic. So it's not some sort of a Python of Java things. It's even not a really a relational database. It's a concept that based on 4 principles: the data ownership by domain, data is a product, data available everywhere, and of course data governed wherever it is. Very important. So I would like to bring you in our case of building a data ecosystem for our flood prediction project. So this is the thing that we started to build at the beginning. We had information on the hydrological network provided by the regional council that fit into a model developed by the TIAO, and then we can provide the information that you have seen so far, some sort of dashboard with the prediction that we can provide from the output of the model. But then it comes to adding more information. Here we want to add the weather information, the rain radar, for instance, and we would like to provide information to a wide range of users, not only the hazards analyst, but maybe more, and with different maybe rules. And then we would like to have, and this is where it's getting complicated. This is why we have to think about this data mesh structure. So is where we jump from the traditional data structure approach to the data mesh approach. So you have seen so far that we pull out the modeling things out of the box of the data mesh structure, and then we replaced with a Kafka that I'm going to show you in a minute, the Kafka Stream Server, which is a framework that allow you to do data mesh. And then you can think bigger. You can add more data for backup or data warehouse where you have access to other data, or you can backup on some of the other data. You can add several other providers as well, because we have a structure now that fits the requirement of our development. So what tech do we use? Very quickly, very shortly, we have here the input and the output. So we can fetch data into from multiple sources, and we can provide information to different data consumer. So what we have in the middle is some sort of engine. So the data mesh solution, it's a scalable framework, and it's based on Docker and Kubernetes. So we have different layers. So the first layer is the storage, the store layer. So it's based on the Kafka for stream processing, Redis and Postgres SQL, just for general data storage, not for the data. Then we have an upper layer, which is what we call the computing layer. And in this computing layer, we have several tools such as Kafka Streams, Faust, and Apache Flinks. So Kafka and Faust, they are for building stream learning, and the Apache Flinks is a data processing framework, which is written both in Java and Python. And on the top, we have, on the left side, we have the Java Hub, the Java Jupyter Notebook environment where we could upload our models and prediction. And on the right side, we have what we called before our dashboards, things using Streamlight and Mercury and things like that. So that's it. At the conclusion, I would like to say that data is the fuel for AI. So we need this data, but what is important before handling a data-driven solution and we want to deploy our solution, it's an adequate data strategy. And I think that if we are going to that way of having a good data strategy for deployment in operational world, in real work, we have to think about validation, verification, and uncertainty qualification. This is very important. But what could increase our way to resolve problem is increasing collaboration and partnership. Thank you very much. I'm really happy to look at your comment and feedback, and happy to make new connection with you and new collaboration. Thank you.
Thank you very much, Phil. What a great talk and sharing your expertise for many, many years. We do have a question, a double question from Jorge, and we have just 1 minute, so please synthesize your answer. The question is, how do you take into account the increasing trend in rainfall amount in the LSTM model?
So actually, that's a very good point, actually. So this is a real-time process of modeling. So that means we are updating the model in real time. Not for instance, if we are receiving a new data every 5 minutes, we are not updating the data, the model every 5 minutes, but we are updating the model often. This is what we need, some high computer power in the background to handle the modeling in real time. Like, for instance, we do it one times every week, for instance, and it takes on a normal computer about 6 hours to provide a new model that we can inject into our data mesh structure. So this is how we can, with the latest data, this is what we can handle new situation, because we know that we cannot predict something that we haven't seen it before, but because it's a real-time process, I thought that we can handle new situation with the coming change in the climate.
Thank you very much, Phil. There's another question from Roland, that we won't have the time to answer live, but I'll encourage you to talk via the hub. Thank you so much for your presentation. Now we finish with the long presentations, 15 minutes each. We have 2 short lightning talks for 5 minutes each with no questions. And then at the end, we have a demo. So I'll encourage you to stretch a little bit if you've been focusing on the presentations. Now is the shorter presentations. And I welcome Lillian Lu, who is going to talk about defining success of a dashboard product with user analytics. Welcome, Lillian.
Kia ora, ko Lillian Lu aho, KESR aho. Thanks for coming to my talk. Let's jump straight in. So what is user analytics? User or web analytics is a way or a tool to measure how users interact with a website or a digital product, such as apps or software. Questions can be answered include who visited your website, when and from where they visited your website, and how they first came to know about it. So why should we do it? Just like many research organizations, at ESR we develop public-facing dashboards to share insights or results. The work is often considered done as soon as we deploy the dashboard. We don't really know how these dashboards are performing. It's probably not even in our nature to answer that because we're here to do research, not selling things. However, if you don't know how these dashboards are performing, it's hard to measure our goals of a project, hard to further develop a product because you won't know where to improve it. Also, when we think about data journalism, such a hot topic at the moment, how would we even do it without knowing what people are interested in? And finally, maybe we do want to sell things. We want people to pay for our science so that we can have more funding to do more of the work that we believe in and love doing. And all of this requires some sort of understanding of your audience, whether they are the public members, other researchers, or even your stakeholders. So you get the ideas now, but how do we do it? Which tool to use? There are way too many user analytics tools out there. I'm not going to go through them one by one, but I will share my experience with the most common one, which is Google Analytics. So this tool is free and super easy to implement. It's very popular, which means your organization is likely to already have some privacy policy about that set up for your company's website so that you don't need to worry about anything. And it's also well documented. However, in this case, Google does own the user data. So if you feel like what they're collecting is sensitive, you may want to consider other tools such as Matomo, but I will not go into it here. So now let's do a quick walkthrough of how to set up Google Analytics in our Shiny dashboard. You can do the same for Python Dash or other web-based dashboards if you want. And you don't need to remember any of this. I just want to show you how quickly this can be done by even one person. So first, you need to create a Google Analytics account and a property. Each property is one website or a dashboard that you want to check, and you can have many under one account. Then you can just let Google know which website you want to track. So copy and paste the website URL, super easy. And then you will get a set of JavaScript code that's generated specifically for this property. You don't even need to know JavaScript. All you need to do is to copy and paste the whole thing and save it as a HTML file and upload it to where you normally put the external files. So for our Shiny, it would be the www folder. And then you just call that HTML file in your UI script for your dashboard, and it will start tracking. So within a few minutes, this is what you will get. You can see how many people visit your dashboard every day, the channels they came from, the device they use, and the locations where they open the dashboard. So you're no longer in the dark. And if you do know some JavaScript, you can also customize what events Google Analytics tracks to understand the user journey better. For example, this dashboard has some filters and they're not defaulted tracking by Google Analytics, even your users are interacting with them. But you can totally add them in, and it's just a few more lines of JavaScript code. And this is what you get. You can see how many actions are fired for the select a region filter or the time button click. And you can even break down to details to see which button that user actually click. So for our dashboard, we have like 12 months as the default button, but so many people are clicking the 6 weeks one. Should we change that default? So that is something to think about. And you can also see if you have a search bar, you can see what people, what address people search, or if you have external link, you can see what links they click to. So that's pretty much it. It's a quick talk, and I hope that I convince you to start thinking about your audience when you do a dashboard product. Let it be your own programming language, program, or utilizing Google Analytics, which is like some existing quick implementing tool. That's all. Thank you.
Thank you, Lilian, and also for sticking to time. We are running here on our second lightning talk by Alexander Petle from NeSI, who's going to talk about how to improve researchers' productivity by using the new NeSI processors.
Hey, kia ora koutou. This is Alexander from NeSI, and I'm going to talk about taking a look at the new processors that we acquired at NeSI and how you can leverage them for your science. So we have a new partition that we have set up, and it's called Milan. So we have currently about 30 nodes, and each node has 128 physical cores. So that means with 2 threads, you're going to have 256 threads per node. This is rather different from the existing Marika nodes that we have, which have 36 physical processors or 72 logical cores. We also have a sort of fast interconnect that connects the different nodes. So I think it's going to be attractive to MPI programs as well as OpenMP programs. OpenMP because you're just going to have so many more threads running on a single node. So the only thing that you need to be aware of is that when you run your Slurm script, you just put all your usual configuration or settings such as time limit and job names and so forth. But now, in addition, you have to specify -- partition is equal to Milan. That's really the only change you have to make. Typically, you won't have to recompile your code because these new AMD processors are binary compatible with Intel. So in principle, because there could be some edge cases where that recompilation might be necessary if your code relies on older libraries or something that we don't have supported on those new nodes. So here I'm showing a couple of performance measures. On the left-hand side, we have the SWAT code. We talked a lot about hydrological software, and that's an example of one. So the blue bar is the Milan, and the orange is the Broadwell. So the lower the better, and so we're getting maybe about 30% or 40% faster execution time. Similar story for other codes. Sometimes the performance improvement is 1.7x. It really varies. We have seen, however, cases where the new Milan would actually run slower than the Broadwell. So just be aware that the performance that you're going to see on these new processors will be dependent on the program, but also on the load of the machine. The other thing that is noteworthy, perhaps, is that you also have a new compiler, the AMD compiler that you can invoke, and you can do a module load AOCC, and it's called FLang for Fortran or CLang for C. And you may want to try that compiler because it has shown to sometimes actually give faster code. So that's about it for me. So more Milan processors. So we're going to, at the end of the day, when the installation is complete, we're going to talk about 64 nodes. We're also going to have more GPUs attached to them, so another 16 A100, 80 gigabytes for those people who are doing machine learning or other workflow calculations. I think that's going to be super exciting. And we want to hear from you, how are these new processors performing for you? And finally, I just want to extend a special thanks, to two people who have helped us improve the performance of these processors. One is Maxime Millen from the University of Canterbury, and his OpenSeas code, as well as Wolfgang Hayek, who's been running the NZCSM, which is a local climate model, the weather forecasting model from NEWA. So thanks very much, and that's it for me.
Thank you very much, Alexander, and also sticking up to time. We are on the last presentation of this session with Helen Morris from ESR, and she's going to present a demo, open source down the drain using R, leaflet and QGIS to track COVID in wastewater. Welcome, Helen.
Hi, thank you. Hi, cool. Kia ora koutou. For Helen Morris tōku ingoa. I work at ESR, and I've been recently working on the SARS-CoV-2 in wastewater project. We kind of wanted to use the geospatial data available to us to hopefully link our wastewater results to reported cases in communities. So at the moment, the Ministry of Health is kind of reporting cases at a DHB level. So we wanted to try and use geospatial data to kind of get to a lower level so that smaller communities can have more information about what's happening in their community. So my demo is going to cover a few tools that we used for doing this. Tools that we used were all open source. So we used QGIS, QGIS, simple features for R, the SP package, and leaflet package. So I'm just going to walk through a few of the steps we did to get our outputs. So first I'm going to show you a video of QGIS. So we often got files from councils that had wastewater pipes. To match the cases to catchments, we needed a polygon area. So we initially started off by using a buffer method. So we'd create about 150 meter buffer around the pipes and kind of use that as our polygon. So this was our kind of initial catchment. This is for Ashburton. A few of the wastewater pipes are available online. So I know all the Canterbury pipes are available online if you want to look at that. We found that this wasn't as accurate. You're kind of getting extra pipes that aren't necessarily connected to residential houses. So we ended up using a method where we download primary parcels and compare them to the wastewater pipes and kind of pull out what parcels are actually connected to these pipes. And you can see, I've zoomed in here, this is where the wastewater treatment plant is. So often a lot of properties along that line aren't actually connected to the system as the pressure's too high. So we've kind of managed to tidy up what cases are actually connected to this system. So next, as you can, sorry. Okay. I'm not sure. Did it change or now? Okay. Yeah. So next we generated tiles in QGIS. So we had, with the wastewater pipes, it's quite a large data set. So we wanted to create tiles for each catchment. So when we load them into any application, it doesn't lag too much or create too much computer usage. So this is just kind of zoom in of some more of the pipes and catchments. So this is all kind of run on the HPC at ESR to generate the tiles because it does take up a lot of computing power. And the next thing, once we had all of our catchments ready, we wanted to add them into a data frame and use it in R. So we used the SF package to convert those shape files into geometries in a data frame format. So we end up having geometries of X, Y, Z sort of dimensions. I'm not sure if my slides are changing. Okay, cool. So now that we've got the geometries for each catchment, we can geospatially join this to some of our site data. So the way that we did this was then we used mesh blocks that are available online, again, I think through Lens, and we used that to kind of connect to our catchments. This way we were able to also summarize cases in each catchment. This was important because wastewater is not actually testing an entire population of a city. It's only testing those people connected to the reticulated wastewater system. So this just kind of shows we loaded in the mesh blocks, and next we used a spatial join to join to the catchments that we had produced earlier. And finally, the last step, we used Leaflet, which is a really popular open source JavaScript library for interactive maps. So we kind of used it in a final Shiny application where users can add their location. And also, if you click on a catchment, you can fly into that catchment and view the map. So I'll just show you the final slide. This is kind of our public-facing wastewater dashboard. So you click View Catchment, and you can zoom in and have a look at what's actually covered by our wastewater testing. Finally, another thing we had as an output was a wastewater report, which is sent to the Ministry of Health every week, and this allows them to kind of see what's happening on smaller community levels in New Zealand, which has been very valuable and useful for tracking how COVID's moving through communities. So I just wanted to say thanks for listening, and especially thanks to my colleagues at ESR, particularly Richard Dean. He set up a lot of this work. Also councils, wastewater providers for providing all the catchment data, and also Mackay. Okay, I think I'll go over this bit. So this is the demo of using QGIS. So we'd often get wastewater pipes kind of sent to us by councils. We needed, obviously, a polygon to actually find cases or connect cases in catchments to that reticulated wastewater system. So we produce a polygon like this. We were using a buffer method, so just created polygon about 150 meters around all of the lines that we had. We found this was kind of not necessarily very accurate, so we ended up using some Lens data, which showed primary parcels, and sorry, I think that's maybe frozen. Yeah, so we used Lens data to kind of compare our wastewater pipes to the primary parcels and select what primary parcels were connected to the wastewater system. I think, yeah, if you move to a different slide. Yeah, so those are the primary parcels there, I think. Yeah, and then once we had those catchments sorted, we created some XYZ tiles. These take up a lot of space. So if you go next slide. So we run that on the high performance, the HPC at ESR, because it takes a lot of memory. You're generating XYZ tiles for hundreds of lines for the pipes. So it just takes up a lot of computer power. If you go to the next slide. And then we used the SF library, and this basically converted our shapefile into usable geometries in a data frame. So we could then use it in R for doing other work, like putting it in a dashboard. Yeah, so if you go next, and then the next slide. Yeah, so we just did a spatial join, joining mesh blocks to those catchments that we had created. Next slide. And the final step we did was to use leaflet in some of our final products. And we were just using this to kind of produce interactive maps in our Shiny apps. If you go to the next slide, I can show you the example. So this is our public-facing dashboard. If you click View Catchment, it zooms into your catchment, and you can see what our wastewater sampling is covering. You can see the pipes. If you go to the next slide, I think that's kind of everything in a nutshell. Another output we had was a report to the Ministry of Health, which just kind of helped them see what was going on at a smaller level in the community. So thanks for listening. Sorry for the issues.
Thank you, Helen. No worries about the difficulties. Everyone has agreed that your work is excellent, and people would like to know more, please contact Helen.
Yeah, I did want to
No.
say I hadn't done any geospatial work before February, so all of these tools have kind of just made it so much easier. And it's all open source, so there's a lot of really cool information out there for people. So yeah, thank you for listening.
Thank you. Thank you for sharing that as well. Kia ora tēnā koutou to all our 7 presenters of this session. We had to extend for 2 minutes to resolve technical issues, but I think everyone has done well, keeping the time, sharing what everyone is doing, and would like to hear more. We'll talk with you via the hub. Have a good lunch and see you in a few minutes.